All right. Welcome to the second lecture on nonlinear data structures. And in the last lecture, we talked about the tree data structure, and we looked at the abstract data type, the motivations for the tree data structure, the kind of applications that we have, and then we went through the whole implementation of the tree data structure. We also saw the code that was written for traversing the tree data structure and to evaluate some expressions. So in today's lecture, we are going to look at a special kind of a tree, which is called a binary tree. And we are going to see that a binary tree carries forward many properties of the tree abstract data type. And it also has additional interesting properties which are very useful when we want to represent data in a binary tree. We are going to therefore explore the binary tree abstract data type today, and really the methods that you see in the binary tree abstract data type are not very different from the methods that you see in the tree abstract data type, except that there are some basic conventions which are very important. And that is what we will be exposed to. In particular, for every node, if it has children nodes, then the binary tree has a special order among them, whereas the generic tree data structure does not mandate an order among the children, though the implementation will definitely and invariably have an order among the children in the tree abstract data type. But in the description of the binary tree abstract data type, the children of a particular node, if well defined, are ordered by the fact that they are the children and there is a special order among them. This is a very fundamental difference. We will study this today. As throughout this course, many of the methods that we implement and specify are going to be recursive, and we will also see that when we state certain traversal properties, we will actually state it using the power of recursion. In other words, whenever we state a certain traversal approach on a binary tree, or like we did in the last lecture on a tree data, on the tree abstract data type, we just specify the behavior of the traversal at a particular node. Right? In particular, we say when we will mark the node as visited and when we will and what we will do it to its children. Right? How we will traverse the trees rooted, the subtrees rooted at the children of a particular node. We will again do something similar when we have to traverse a binary tree. We will actually state the order in which the children of a particular node are visited and the order in which the subtrees rooted at the children are traversed. Therefore, we take recursion time and again, and this is really a central theme in any data structures course, that you must become comfortable with the usage of recursion and you must be able to understand recursive specifications. So now let's go to the slides. So the lecture pattern will more or less be similar to what you have been seeing so far. We will look at the slides, then we will look at the code, and then we will have a quick short run. And I would like to draw your attention to the fact that the description of the C programs that I have written, I have reduced the time that I spent on the descriptions, because by now you must be comfortable with more or less understanding what the C program should be doing by understanding the slides itself. Another very important point that I will draw your attention to again is when you look at the C programs that I present to you, you will see that the C programs, the interface functions and the methods are all broken into pieces of code which typically have a few statements maximum. You will see that many of them have 1 or 2 statements and some of them have 4 to 5 statements. Right? So this is kind of a thumb rule. If you're creating an abstract data type, then it's important for you to understand the abstract data type and understand its methods in such a way that you will be able to implement each method using very few statements. Right? So this is a very, very important thing. And really there is no specification as to what few is, but as a student programmer, I would say about most programming exercises that you see either in a programming competition or in a course assignment, you should be able to write down every method using not more than 10 statements. So that should typically be your goal. Right? All right, so let us go to our slides and more on that as we go along. Alright, so let us go to our slides and more on that as we go along. Alright, we are going to look at the binary tree abstract data type. This is our lecture number 16, and this is the description of the tree abstract data type. I am sure you recall most of it. There are generic methods which tell you the size of the tree, which means it tells you the number of nodes in the tree, whether the tree is empty, and the most important thing, the reason I am repeating this part is to draw a distinction between these two. The elements method lists all the elements which are in the tree. The positions method lists all the positions or all the nodes in the tree, right? So now, of course, the output of the positions method is not clear, right? All that you have to imagine is that the position method returns to you a list of pointers to individual positions in the tree or the individual nodes in the tree. I repeat this, the position method will return a list. It will be a list of positions, and every element in this list of positions will be a pointer to a node in the tree. We don't really implement these in the C programs that we talk about, but all these are extremely easy to construct. Then you have accessor methods which give you nodes, or in other words, these are all positions. Parent of P returns a pointer to the parent of the node P if it is well defined. Children of P returns a position list, which each element in the list is a pointer to the children of P. The query methods are properties of every node, whether it is an internal node or an external node. The update methods are the ones that deal with the values which we store at different nodes in the tree. Therefore, the most important thing that I am repeating in this module is that there are two kinds of objects that you manipulate in a tree abstract data type as a programmer. One is the structural aspect, that is, you manipulate the pointers to maintain the tree-like structure. Second, you manipulate the values which are stored in the nodes. Therefore, it's very important to keep this distinction in mind. Therefore, tree is a structural property, right? And the data which are organized in the tree, right, are the ones that you want to manipulate, and those that you want to access and update and modify, query, and so on and so forth. So this is the story of the tree abstract data type. What is a binary tree abstract data type? First of all, the binary tree abstract data type has all the methods and the properties associated with the tree abstract data type. Apart from this, it has additional methods, position methods, which now tell you the left child and the right child. Therefore, if P is a node, the left child is a pointer to a special child, right, which is called the left child of P. And the right child is a pointer to a special child which is called the right child of P. As you can see now that by the definition of these additional methods, as I have just specified them, every node has at most 2 children. Such a tree is a binary tree. Therefore, the property of the binary tree abstract data type is that it has all the methods and the data items associated with the tree ADT, plus it has 2 additional methods, one for the left child of P and one for the right child of P, and it is possible that either exactly one of the 2 left children are well defined or neither is well defined. Another method that we have is a sibling of P, and if you notice what I said the sibling of P. Right? Therefore, recall that in the tree abstract data type, the sibling would be a listing of nodes. It would be a position list. On the other hand, very importantly, the return value of this particular method is a pointer to one another node. In other words, it is a position. Right? Therefore, let us just recall the structure of a binary tree. It is a tree, first of all. It has all the data and the methods associated with the tree. It has 3 additional methods, right, which essentially place further restrictions on the structure of the tree. Right? So every node has at most 1 left child, at most 1 right child, and every node has at most 1 sibling. The update methods may be defined by the different data structures. We will actually see in the next set of lectures something called a binary search tree, and we will look at the heap data structure. Right? And both of these will have their own update method implementations. In particular, we will be able to update the values in the different nodes. We will be able to delete certain values. We will be able to delete certain nodes, and so on and so forth. Let us look at some examples of a binary tree. The best way to understand the distinction between different concepts is to look at a few examples. Let us look at a skewed binary tree. Right? It is called a skewed binary tree because if you notice, for every node here, one of the children is missing. So this is also a binary tree. A is the root of the binary tree. B is its left child. Right? C is the left child. D is the left child of C. E is the left child of D. In this case, a different skewed binary tree. A is the parent of B and B is the right child of A. On the other hand, this is a complete binary tree. A complete binary tree is one in which every internal node, that is, every non-external node, has exactly two children. I repeat, a complete binary tree is one in which every internal node, otherwise a non-external node, observe that E, F and G are external nodes, H, I are external nodes, they have 0 children, whereas D, B, A and C have exactly 2 children. This is the distinction between a skewed binary tree and a complete binary tree. Now you can ask yourself a very important question. Right? What is the depth of a complete binary tree? And if you have two paths, one from the root to this leaf and one from a root to another leaf, what can the depth of the two leaf nodes, how much can they differ by? This is an interesting question, right? And you can ask yourself this question. We will visit this in a couple of lectures from now. Let me pose the question clearly. The depth of every node is a well-defined concept from the previous lecture. In a complete binary tree, what can be the largest value of the difference between the depth of two leaf nodes? Okay, now comes the concept of the fundamental difference between an element of the tree abstract data type and an element of the binary tree abstract data type. The subtrees of a binary tree are ordered. Right? In particular, we say that B is the left child of A. In this example, I say that B is the right child of A. Right? Now, these two trees that we have drawn are two different binary trees. In this binary tree, B is a left child of A, and in this binary tree, B is a right child of A. On the other hand, when we view this as trees, both of them are the same. B is just a child of A, B is just a child of A. Right? Therefore, the sibling relationship, right, from the concept of the ADT really does not exist. Similarly, the child relationship, being the left child and the right child, does not exist when you define a binary tree. Does not exist when you define an arbitrary tree. When you implement, there will be the first child, the second child, and the third child, and so on, because we keep track of the leftmost child, right sibling. We call the leftmost child right sibling representation of a tree. So in the implementation, there is a well-defined ordering of the children. But in the specification of the abstract data type, we do not have any such mandate to have a ordering of the children. Whereas in a binary tree, we definitely have an ordering of the at most two children of any node. Here is a data structure for the binary trees. This is an implementation or an in-memory view. This, on the other hand, is an abstract view in the mind of a programmer or a designer. This is the in-memory view in the mind of a programmer, right, or the person who is coding the whole data structure or who is writing the program for setting up the data structure. Now what we have is a node, right? The nodes are of two colors, as you can see. The violet colored or the pink colored nodes are all external nodes, otherwise the leaf nodes, where both the left pointer and the right pointer are null pointers. Right? There is a value field which has a value A, and for the sake of efficiency, we also store a parent pointer. The parent pointer for the root node is that the parent pointer points to null. Right? As usual, we have an element, a pointer to the parent node, a left child node, and a right child node. So now you can ask yourself the question, what is the sibling of D? The sibling of the node containing D is the node containing A. In particular, you can say that the left sibling of the node containing D is the left sibling of the node containing A. Similarly, the right sibling of the node containing A is the right sibling of the node containing D. Now let's move on to binary tree traversals, and as you can see, I'm using the power of recursion to actually state this in a very crisp fashion, right? Let us assume that L, capital R and small r stand for moving left, visiting a node and moving right. Therefore, for the recursive specification of the different kinds of traversals, there are 6 possible rules that could be followed. You first explore the left subtree, then you mark the current node as visited, then you visit the right subtree. Or you visit the left subtree, you traverse the left subtree, then you traverse the right subtree, then mark the node as visited. Now, the third possibility is mark the node as visited, then you traverse the left subtree, then you traverse the right subtree. Observe that the traversal is specified recursively. The word traversal is used recursively. Therefore, there are 6 such possibilities. As clear, there are 3 factorial. There are 3 possibilities, right? Left, right, and capital R, right? That is to visit the node. And these can be done in 6 ways, which is 3 factorial. 3 multiplied by 2 multiplied by 1 possible ways. If we adopt the convention that we traverse the left before the right, only 3 traversals remain. Right? What are the 3 traversals? First, you traverse the left subtree, then you mark the current node as visited, then you traverse the right subtree. This is called in-order traversal. If you traverse the left subtree, then the right subtree, and then mark the node as visited, then this is called post-order traversal. If you mark the node as visited, then you traverse the left subtree, then the right subtree, then we have the pre-order traversal. Observe that when we talked about traversals in the tree abstract data type, we really did not talk about the in-order traversal, right? And on the other hand, we did talk about the post-order traversal. So let us just look at the code for the in-order traversal, and this is what will be more or less implemented in the C program. Okay? The numbering associated with the nodes in the tree tell you the order in which they are printed out by the in-order traversal. Right? So what is the rule for the in-order traversal? You start at the root, you traverse the left subtree first, then you mark this as visited, then you traverse the right subtree. That's exactly what it says. If the node is internal, then you do an in-order traversal of left child of V, you visit V, and if it is internal, then you perform a in-order traversal of the right child of V. I think this if is internal is not required here, but it doesn't matter, the code is indeed correct. So let us just look at the order in which the nodes will be marked as visited. The first node to be marked as visited will be 1. Then 2 gets marked as visited. Then 3 gets marked as visited. Then 4, then 5. Then it is 6. Then the right subtree of the right child of the subtree rooted the right child of this node, the root node. Okay. And that you can see will be marked as 7, 8 and 9 respectively. This is the in-order traversal. So let's look at one more traversal, and the code for this follows in the next slide. We have not yet implemented this to show you in the C program, but the picture is very clear. It's a nice traversal of the binary tree, which is very interesting. You visualize the tree with the root and you run a pencil over the tree edges starting at the root. That is, you start from here and you run a pencil, okay, and visit every edge without lifting the pencil from the paper. As you can see, the mouse pointer is moving exactly the way the traversal is supposed to happen. So now you will see that every edge is visited twice. Let us just look at a small function description. This is called the Euler-Tour traversal. So perform action for visiting node to the left, right? And if V is internal, then you perform a Euler tour recursively at the left node. Then you perform the action for visiting the node from below. Then if it is internal, you move to the right and you perform the action for visiting the node to the right. And this will be done recursively. Right? So let us just do this again. Right? So you visit to, right? Then you come back to the route, then you go to the right hand side and visit this. Right? So one can also visualize this walk as being done by the in-order traversal of the tree that we just looked at. So what we did just now was to look at the binary tree abstract data type, and you would have observed that the conceptual differences between the binary tree abstract data type and the tree abstract data type is in the fact that a binary tree, the children are at most 2 in number and they are ordered, and as a sibling relationship, every node has at most one sibling, it has at most one left sibling or at most one right sibling. Okay? And we also saw that one can visualize a new traversal of a binary tree, which is an in-order traversal. Okay? And from the presentation, you would have also noticed that the in-order traversal also gives you an idea of the order in which expressions are evaluated. Okay? So if your tree was an expression tree, as we will see in the next lecture, the order in which the tree is evaluated is essentially using a in-order traversal. Let's now move to look at the programs that we have written, right? And quickly go through the programs, because what you see in the C programs now is exactly what we saw in the slides, except that we can compile them and execute them. So as you can see, I have written 4 pieces of code, 2 .h files and .c files, right? So binary tree.h tells you the corresponding basic data type, the ADT structure, the node structure for the binary tree, right? And then we have the binary tree methods, right? And these methods are an implementation of the ADT methods associated with the binary tree. And then the interface functions are what are included in the C file, right? And the binary tree methods is compiled to give a .o file. So let us just quickly go through. Okay. Fine. So here is a node in the tree, right? You have a data item, you have a pointer to the parent, you have a pointer to the right child, and you have a pointer to the left child. Okay. And this is called a node. Right. Now we also have a type called the tree, right? I call it a binary tree, right? It is comprised of a root node and it has a data item which is the size. Okay? So therefore, the tree itself is just the pointer, okay, to the root node of the tree. So this is the structure of the binary tree, right? So this essentially tells you what the data looks like. Let us look at the interface function. All right. Okay, so you include binary tree.h, right? And this is a method to create a tree or instantiate a tree. Right? It just creates one node, right? And basically initializes all the pointers appropriately. These functions are the generic methods that we have seen, the accessor methods, which gives you pointers to different nodes in the tree, the pointer to the parent, pointer to the root. And these are query methods, structural query methods to ask whether a node is an internal node or an external node. These are Boolean queries, as you can see. And here is a query as to whether a node is a root of a tree or not. This is to check if the parent pointer is null. Here we delete nodes. Here we insert into the tree T a node n as the parent, with this as the parent. and the in-order, pre-order and post-order traversal are also implemented, given a pointer to the root of the particular tree. These are the interface methods. Let us look at the Let's quickly run through the constructor function or the creator function. The create tree function, right, creates a binary tree. It says that the root value points to null, right? The tree is empty, there is nothing else. The tree is empty by setting tPointer.size is equal to 0. Right? The size function returns a value of tPointer.size. The tree is empty when there are no nodes inside it, when the size of t is equal to 0. As you can see, that each of these functions are very important, and they are just single statements. To get the root of a tree, you just return a pointer to the root, and to get a pointer to the parent of a particular node, you return the node pointer.parent. To check if a node is null, you check if either the left child is not null or the right child is not null. Observe that a single logical expression takes care of this. And a node is external if it is not internal. This is nicely captured in this statement. If something is a root, then its parent is null, as I said earlier. Now let's look at the delete function. So let's look at this function carefully and then move on, because this is the most crucial new thing in the implementation from the last lecture. So you want to delete the node n. Right? So to delete the node n, what we need to do is we have to first keep track of the parent of this particular node and look at the child and look at the children of this particular node and connect them appropriately. So let us just see this. If the node is external, then there is no work to be done. Target is null. Okay? Then the delete function will delete it. Okay? If the node has a right child, then the target is taken to be the right child of the node. Otherwise, it's taken to be the left child of the node. And observe that implicitly, if a node has both its right child and left child, we do not specify completely what the deletion has to do. We will see this in a subsequent implementation of binary search trees. Okay? But in this code, we always delete a node if it is either a leaf or has exactly a left child or has exactly a right child. The picture is quite clear. If it is a leaf, no work needs to be done. It can just be deleted. And if it is really the left child of its parent, right, then the left child of the parent now points to the left child of the or this target, depending on whether it is the left child or the right child. The same thing here. If the node being deleted is a right child of its parent, then the right child of the parent now becomes the target, which is the single child of the node that you are deleting. Right? So let's just go through this again. The convention here is that we will delete only nodes which have either 0 or 1 children, right? 0 children or 1 child, right? And if it is 0, no work needs to be done. Right? We need to program this more carefully, but just to show you a implementation, this has been quickly done. And if it has exactly 1 child, then that single child is stored in this variable target. It is a pointer, and the left child or right child of the parent is then set to target. This way, the node n is no longer in the tree. Insert again is fairly simple, right? So what we do is we insert the node, right, based on whether it is the left child or the right child of the parent. So the position value tells you whether the node n has to be inserted as a left child or right child of the parent, and here the assumption is that the programmer takes care of carefully inserting it by giving the appropriate values of position. So depending on position, if the position is 1, then you insert parent pointer to the right child as n, and otherwise we insert parent pointer or left child to be the node n, and the parent of the node n is given to be parent, and the size of the tree is increased. Right? Observe that the only place the node gets inserted is at a leaf node. Of course, this is not checked here. This is the job of the insertion function. Whichever function is doing the insertion has to do this carefully. It has to find the leaf and ensure that node n is the appropriate leaf or a node with exactly one child, right? And find the parent, right, which has either 0 children or exactly one child, and insert it based on the value of position. Right? Let me repeat this. Right? So this insert function inserts it into a tree, right? Inserts n into a tree as a child of a node called parent, right? And n will be inserted based on the value of position. The value of position will be either 1 or 0, right? And if it is 1, n is made the right child of parent. If n is 0, it's made the left child of parent. And the size of the tree is incremented appropriately. It is the responsibility of the calling function to check that this implementation is used meaningfully. Here are the traversals, which are fairly straightforward. The inner traversal, as you can see, is a listing, right, where we just print out the value at different nodes in the tree. Right? So as you can see, we traverse the left child, then print the root, then traverse the right child. Whereas in pre-order, we print the root, traverse the left child, then traverse the right child. In post-order, we traverse the left child, then traverse the right child, then we print the root. This completes the implementation of all the methods associated with a binary tree. Let us look at the example exercise. So the exercise here is to create a tree, right, and populate the tree with an arithmetic expression. Right? So the expression, as you will see, right, is the following: the root is a plus, the left child is a star, right, and to the left of the left child we insert the value 0, right, and at the right of the root we create the star, right. So as you can see, at the left of the node we have the multiplication operator, and at the right of the root we have the multiplication operator again, right? And then we populate values in the tree, right? And we have essentially hard coded a simple arithmetic expression. What you can definitely do is to write a small function which will read from the input an arithmetic expression and construct this tree. The more important thing is the evaluation. Let us just take a look at this. The evaluate expression is a recursive function. You will see that it evaluates the expression at the left child, then evaluates expression at the right child, takes the two values, and depending on the operator which is present at the root, then it performs the appropriate arithmetic operation and returns it to the calling function. So it's a recursive function which evaluates the expression, right, in the order in which we evaluate arithmetic expressions which are given in the normal in-order parenthesized form. Right? So you evaluate the left expression first, then evaluate the right expression, and then add it. So this is exactly the evaluation that we do by hand when we look at a arithmetic expression. In this exercise, we assume that the arithmetic expression is stored in a tree, right, to which we have access via the root pointer, and then we evaluate the expression. As you can see, the evaluation is a post-order expression. So let's just compile all these things, GCC minus C binary. So this compiles the file of binary tree methods. Then we compile the program, which is a toy program making use of all the functions. Now we use the object file that we have created. Now the compilation is done and the executable is bin eval, and the value is 14 for the expression that is hard coded. The value really doesn't matter. Let me just take you back to the if you look at the code, we have used almost all the functions which we have written in the interface file. We have checked if a node is an internal node or an external node. Okay. Then we have access to the data items left child, right child, and parent. Then we use the create tree method, right, which is a method to create a tree, instantiate a tree. And we use the insert function, right, which inserts a node into the tree. And finally, we evaluate the expression by traversing the tree carefully and using the methods that we have implemented along with the binary tree ADT. All right, so that brings us to the end of this lecture on the binary tree abstract data type. As you can see, we have now a clear understanding of the distinction between a tree and a binary tree. Okay? And this distinction is very important because the binary tree has some very important order information as part of the abstract data type itself. And this is extremely important to understand. Binary trees are used to store arithmetic expressions, and binary trees are used to implement the BODMAS rules that we study in school, the rules to evaluate arithmetic expressions in a uniform and consistent fashion. In the next lecture, when we meet, we will use all these methods that we have seen so far and write few quick programs for expression evaluation and other such exercises. That brings to an end today's lecture. Thank you.